Welcome. Let me say something about the work of Jessie Pitsillides, senior thesis done this spring in the math department in the area of linear algebra. One of the questions one can study is when are two matrices similar, and we learned that trace or determinant or eigenvalues are invariants, but we want to have a complete set of invariants. First question is, find a complete set of invariants for this equivalence relation. And the answer is given by this theorem that we can look at the rank patterns. It's something which is stressed also in the book of Otto Brecher, linear algebra book of Brecher, that we not only look at the ranks of matrix, but the ranks of the powers, which are also invariants. And these are really in a complete set of invariants for similarity. Something which Poning Chen and I were pondering in 2008 when we taught linear algebra, and we could not answer it then. Jessie answered it, but later we found it is actually a known result. And it's quite explicit, so Jessie gave a complete answer here, even explicit answer we can get from the rank patterns. The rank patterns are just the rank of the a minus lambda to the k powers. These rank patterns determine the structure of the Jordan normal form. Very nice result. I want to explain this quickly. But another question is how many equivalence classes there are if we look at this weaker equivalence relation. So we can look at the structure of the Jordan normal form matrices, and we don't look at the eigenvalues where they are located, but just the form of the Jordan normal form matrices. For example, for 4 times 4 matrices, there are 14 different types. And this has actually been of interest in the context of bilinear forms of algebraic geometry. If we look at invariants of pairs of quadrics, something we also teach in calculus when we do Lagrange multipliers. So we have 2 quadrics and we want to see what type of singularities you can get, and if you want to count that, you want to classify that. It's also a more than 100-year-old topic. In that context, this has been studied very much. And so we know here this is 14, and which appear here are the partitions of partitions. A very nice thing. I love partitions. This is the generating function of the partition. This is the generating function of the partitions of partitions. They also form we can look at partitions of partitions as kind of numbers, and we can add them, we can multiply them. It's a nice commutative ring structure, and so these numbers are interesting from the combinatorial point of view, and they appear here just as the number of types of matrices or types of Jordan normal forms. Also this Jessie answered on her own, and it turned out that this has been studied already very, very early, actually already by Sylvester in 1854, which is even before matrix algebra was born. It's very interesting fact that one has studied linear algebra before matrices were born. Matrix means the mother of determinants. Determinants have been studied earlier, and determinants matter when you look at the structure of singularities of tangencies of quadrics. So this is a classical topic in linear algebra. It goes into combinatorics and has relations with algebraic geometry, classical algebraic geometry. Segre, for example, which appears here. Segre characteristic is a characterization of the Jordan normal form structure. This Segre characteristic bears the name of Segre, Benjamin Segre, who was an algebraic geometer. So this is interesting. Let me just say something about this explicit way how you can get from the rank patterns, how you can get the structure of the Jordan normal form, and it's very nice because it is a little bit of combinatorics. So here we have an example of a matrix, a 7 times 7 matrix. We can of course just restrict to one eigenvalue and then look at the structure here which we have. So in this case there's a Jordan block, a 4 Jordan block, a 2 Jordan block, and a 1 Jordan block. We don't know this Jordan block, but what we know is the rank patterns. That's what we measure. We measure what the rank is, and we take the 0th power, 1 power, 2nd power, 3rd power, 4th power, and then what we can do is we can turn this and get the kernel patterns, which is just 7 minus. So 7 minus 7 is 0, 7 minus 4 is 3, 7 minus 2 is 5. This is called the kernel pattern. And then what we can do is we can take the derivative, discrete derivative of this. So 3 minus 0 is 3. 5 minus 3 is 2, 6 minus 5 is 1, 7 minus 6 is 1, and this now forms a partition of 7. So this partition 3, 2, 1, 1 is a partition of 7, and this partition of 7 is visualized here with this Ferrer diagram. It's like a Young diagram, but it's called here a Ferrer diagram. And we don't look at numbers in the Young diagram. So this is 3, 2, 1, 1. Now we can turn this around. This is an involution and a kind of a symmetry among partitions, which we can do. We can just turn it around, and then we get the dual partition or conjugate partition, which is in this case 4, 2, 1. And 4, 2, 1 is really the structure of the Jordan normal form. That's all I wanted to say today.